Hey, so welcome to the latest stream of the B project. We've got a few people on the stream at the moment. We've got Thibaut. We have Alex.
Hey guys.
And I think that's it. Yeah, that's it. So today we're going to be working on a new addition to the Tangle, which is an eviction system. So I can give a bit of an example of what's going to be going on. So I've just got a little paint app here. It's easier to explain. So obviously the Tangle is quite large and it's composed of many transactions. And so we can't really keep all of it in memory at once. So you'll have all of these transactions all connected to each other and so on. They end up creating this sort of web of nodes that's quite complicated. It's a lot of data to move through and sort. And so what we do is we have an in-memory cache for things that are accessed a lot, and then the rest of the Tangle goes on disk. So the idea behind this is that things that we need fairly rapid access to get put in the cache, and things that we don't need so rapid access to get put on disk. So there comes an interesting question here, which is, when do you decide to move things from the cache to disk? And so the system that sort of designs this, or the system that determines this, is called a cache evictions strategy. So we're going to be implementing a simple one at the moment, which is called last read evictions strategy, or rather least recently read. So when we access a node in the Tangle, it's going to push it onto a priority queue, and then when our cache becomes full, we're going to take the top entry off the priority queue and we're going to move it to disk. So we'll end up with this big list of things, or rather transaction nodes in order of when they were last read, and every time we insert a new thing into the Tangle, we're going to pop the last one off as we insert the most recent one. And as we read entries in the Tangle, we'll be moving them all the way back up to the top in order to refresh them. So for this, we're going to be using a crate Rust library called LRU. Wrong one. Which? One moment. There we go. So move this off now. So we're going to be using this crate called LRU, and it's actually a copy, or not really a copy, but it's heavily influenced by the implementation that used to be in the Rust standard library, but it was removed due to various decisions. It was deemed to not be useful enough, and so it was moved out of the standard library in order to keep it quite simple. So we're gonna make use of this now. So I'm just going to open up my editor. Here we go. So first of all, we're going to start using the crate. So to do that, I'm just moving things around at the moment so I can actually see things. So to do that, we're going to add it as a dependency. So LRU.
No, I can't hear any.
Sorry, what was that?
Maybe he's a chat.
Hello? Can you hear me? I think Discord might be playing up, so I'm just going to reopen it.
Maybe he looks at the chat.
One moment. It's fun when technology doesn't work.
The viewers
Right.
can still hear him. So
Am I back now?
if I
Josh, you're
Hello?
back?
Am I back? Can you hear me?
Yeah.
Yes.
Okay, great.
yes.
Right, we're back again.
Yeah,
I think
so
my
we
Discord
couldn't
crashed.
we couldn't hear you for like 2 minutes.
Right, so we're going to add the LRU dependency. So you're going to use the latest version, which is 0.5. And so what we're going to end up with is the LRU crate allows us to define a mapping between some sort of ordered key and some value. So in this case, we already stored the transactions themselves elsewhere, and so the value we're going to be mapping to is going to be the hash of the transaction itself. Later on in development, we'll be replacing this with an index-based system, which will mean that lookup will be even faster. But right now, we're just indexing things via the hash. So we're going to import the type we want. So LRU, as mentioned previously, means it means that the latest item is going to be the one that was most recently read from the tangle. So I might change this field name later. Actually, cache queue, that'll do. Okay, so the key we're going to have is some kind of uniformly increasing counter. So when we decide to read a new entry from the tangle, a new transaction, we're going to increase this counter, and so the transaction is going to be pushed to the top again. Right, so we have the data structure that we need. So cache queue, right, so let's just check that compiles. And it looks like it's going to be checking a lot of crates. So in the meantime, I'm gonna create a few more things around the side. So what we're going to want is we're going to want a counter that's going to be increasing every time we read an entry in the cache. So this counter is going to be increasing, but we've got a bit of a problem here. So we want to increase this counter every time we call the get method. And this is going to be a bit of a problem because the get method, it takes self-immutably, which means that we can't mutate anything in here. So there is a solution to that, and that is to use an atomic counter. An atomic counter can be updated immutably because it's done instantaneously or effectively instantaneously, and so doesn't create a data race. So we're going to import the type needed to do atomics. So here's our type. So we're going to start off with the counter at 0. So then we're just going to add a little method. Let's put it, where can we put it? Let's put it down here. Let's call it generate counter, generate cache index, and it's going to produce a U64 for us, so a 64-bit unsigned integer. So we're going to do self.cache counter, and there's a method on an atomic integer called fetchAdd, and what this does is it adds a number to the counter and then returns the old value. So in this case, we just want to increment it. It's going to return the old value here, and so we're going to end up with the U64 being returned. So let's take this and let's use it to insert an entry into the queue. So we're going to do, let me just do some Googling, or not Googling, some looking at documentation. That's the more official term for it. Okay, so what we're going to do is we're going to get the entry that corresponds to our hash. I think I've messed this up a little bit. I think, yeah, so I'm going to be changing this a little bit after the call, so the implementation is going to be changing a little bit, but this will do for now. So instead we're going to index things by the hash. Actually, I think this crate might automatically handle the counting. Yeah, so one thing we're going to be doing at a later date is switching out the LRU crate with something that lets us manually control things. Actually, we might not need to do that. Right. I'm going to put this in there instead for now. So we've got our counter, we've got our generate cache index function, and so now when we want to update this entry, we are going to we're going to use get mut and we're indexing by the hash of the transaction that we want to update. And what we're going to do is we're going to update the priority with our new cache index. So this is going to allow for an optimization at a later date, and this optimization is quite important because we don't want to be constantly updating the priority of a transaction whenever we try to get it, because that can be a fairly expensive operation, and if we're repeatedly trying to get a particular transaction, then that's going to have a bit of an effect on things. I'm just going to check the chat. Okay. So to improve on that, we're going to use this cache index to see how far down in the cache our transaction is, and if it's fairly close to the top, then we're not going to bother updating it. And that's a thing that I'll implement in a bit. And the reason for this is that if the transaction is quite close to the top of the cache anyway, it's not in danger of being evicted from the cache anytime soon, and so we don't need to care. Unless it's really close to being evicted, in which case we want to make sure it doesn't get evicted. So I'm going to implement that in a while, but first I'm going to, let me head back here. Right, we're going to do, and if there is no entry in the cache, we're going to insert one. So let's just check to see whether that compiles. I'm sure there'll be a problem somewhere. Yeah. Okay, it doesn't implement default, that's interesting. A bit odd as well. Oh well, that's fine. Okay, we're going to give it a capacity. So for now, let's give it a capacity that we define as a constant. Of course, we can change that depending on the memory space that's available to the user, or to the program rather. So let's go for something fairly simple. Let's go for 2 to the 16. So in the future, of course, we'll be expanding this, but right now I don't want to be in any danger of crashing my computer by trying to fill the memory. So, oh yeah, I'm doing something ridiculous again. Okay, so the annoying thing is that the LRU cache crate, it doesn't have an entry API, which is how I do this normally. So normally I do something like this. Normally I do something like that, which makes it a lot easier to either insert a new entry or update the existing entry. But because that isn't the case, at the moment I'm just going to do this to insert, to either insert a new entry. Actually, let me move this around a bit. So what we're doing here is we're trying to fetch the entry from the cache queue, and if there's no such entry, then we insert a placeholder, and then we get a reference to that placeholder, and otherwise we just use the entry as is. And so now we know that the entry is definitely filled, because either it hits this case in which the entry exists, or it hits this case, in which case we've just inserted an entry anyway. So we can now do now give it a new cache index. And we're also going to want to move this because we only want to update it if the transaction is actually in the cache. So now we're going to get a borrow error. So, in fact, I'm going to show you the borrow error that we'll get. I'm sure there'll be the other errors I need to fix first. Oh, yeah. So, that's a simple one. So we only need to use what's called a relaxed ordering atomic here. So we don't care the order in which these atomics are executed. The only thing we care about is that each one is unique, and that's going to happen anyway because the increment is atomic. So we're always going to get a unique number. And that's basically for those of you that understand what atomic ordering rules are. They can be a bit complex if you don't really have an idea of what a cache line is and how caches interact in a CPU. So yeah, now as expected, we're getting a borrow error. So the reason for this is that here we're borrowing self, and here we're also borrowing self, effectively a field of self. So what we're going to have to do is we're going to have to take a reference to it initially. We're also going to get another error, which we'll which we'll get to. Right. Yeah, so, and the original error that we're going to get is that our cache is not mutable, or rather, we can't mutate the cache here because it's behind this reference, or rather because it's behind an immutable reference. So what we're going to need to do is we're going to need to wrap this in some kind of primitive that allows us to update it without a data race occurring. So in the long term, we might, we'll probably go for a lock-free data structure. But for now, it'll be a lot easier to go for a solution like a read-write lock. So a read-write lock is something that allows us to have unique access to a piece of data, even if we're accessing the piece of data with different threads. So now we don't even need this bit. Actually, no, we don't need this bit now. So, here we go. So just a few extra errors from Rust, because it wouldn't be Rust without mutability errors. Right. So that seems to work. Now we have to have now we need to do one last thing, which is to make sure that we insert an entry when we insert an entry into the cache. So we have a method somewhere here. Here we go. We have a method here that inserts a new entry into the cache. So along with that, we're going to okay, that seems to work. So the next thing we're going to want to do is we're going to want to create a test for this. So what I'm going to do is I'm going to create a way of creating a tangle with a specific capacity, but I only want this to be accessible from tests or from test code. Yeah. So now we're going to create the LIU cache with a specific capacity. excuse me, I've got a sore throat. So we're going to use this capacity that we pass to the tangle, and so we're going to use this to test the cache eviction in some test code all the way down here. So the first thing we're going to want to do, let me get my bearings a moment. Okay, right. So there's one thing we've missed at the moment, which is that we want to also evict things when the cache gets a bit too full. So I don't believe we currently have a way to remove entries from the cache. Let's see. No, we don't currently. So we're going to want to evict on insertion. So when we insert a new node into the cache, we're probably going to want to remove an older node. So we're going to create this new function, and what it's going to do is it's going to attempt to evict things if there is a call to evict them. So we're going to evict if the cache reaches its maximum capacity. So probably be changing this at a later date, but for now, it should work. So we're gonna pop the last recently used entry from the cache queue, and we're gonna take a look at the hash. This is. Okay. There might not be an entry in the queue at the moment, so in that case, or rather, there will be because the cache is already filled. So what we can do is we can just effectively unwrap here. So now we can get to the job of removing that entry from all of the other fields in the cache. So we're going to want to remove it from here, and from here. And also from the cache queue itself, of course, although that's already been done now since we've just popped it. So vertices, children, and tips. Going to find the correct entry in the documentation. There we go. that. I'm just going to turn off that alarm. And I'm back. So we're going to remove the entry from all of these data structures, but we're going to want to expect that there's an entry in there. Because if there's no such entry in there, then something has gone badly wrong, and we want that to be visible to the user or to us as we're developing it. Okay. Let's check that.
Yeah, I'm not sure I would expect it on the tips. I'm not sure it's necessarily in this one.
Is that the case? Is it not always there?
It's not always there.
Okay, that's fair enough then.
Dom is asking what's your editor?
Oh, my
Josh?
editor is it's a bit of a weird one. It's called Howl. It's sort of kind of half keyboard driven, half not. I don't know. I never really got into Vim, and so I just ended up using this one.
Yeah, nobody really gets Vim.
I mean, I'm told I probably should get into Vim at some point, but
Yeah, you should. You
never
should
got around to it.
definitely.
You should not.
You should not do Emacs. That's for sure.
Alex, do you know whether children will always have an entry for each transaction? Is that the case? It might not, mightn't it? Yeah, because we might have orphan transactions that don't have children, so I'm going to remove the expect from there and just keep it on vertices.
Yeah, but maybe it still exists, but it's empty.
Yeah, exactly. I think that it exists, but the hash set is empty.
Okay, is that always
But
the case, is it? Okay, well, we can try it, and then if it fails, then, well, at least we know it fails, and we can correct it. So,
Yeah, sure.
No problems.
I think it exists. We have to look at the insert function for that, but yeah, I think it exists. It does add child, and if the entry doesn't exist, then it creates it.
Sorry.
Look at the add child function, then I think it will create the hash set, but just not put anything in there. But yeah, that would be. So if it's vacant, then it creates it.
Okay. Well, that's all fine then. So that should, in theory, work. So I'm also going to add a few other functions used for debugging, like actually, no, I'm going to leave that for now.
Maybe the width capacity. Maybe the width capacity one shouldn't be test only.
Yeah, I mean, I guess we can make it public, can't we? Because yeah, that might be useful.
Yeah, that's probably the way we are going to construct it from a configuration variable anyway. So
yeah, that's fair. Perhaps in that case we should just and then remove this entirely. Although 0 is a stupid capacity to have by default, isn't it? That's not very clever. Yeah, I'll just keep it like that for now. I'm sure we can find a better way later.
Yeah.
A 0 capacity tangle, so useful. Right, okay, good. We have a create random transaction function there. That's extremely useful. So I'm just going to call it a few times. Create, let's say 3. 3, 10, what's the difference? Right, so that's creating us a few transactions. And the next thing we're going to want to do is to insert them. Hash was on the left, wasn't it? Actually, it's alright, I'll leave it there for now. Tell them on a live stream because I'm messing everything up at the moment. Okay, that should be fine. So we're also going to give it a capacity of, let's say, 5. And once we've inserted all of these things, in theory, once we get to the 5th entry, it should start removing them. So I'm going to assert that tangle dot length. We probably don't have a length function, do we? No, we don't. Okay, I'm just going to create one.
Wait, are you sure we don't have that?
I
I'm pretty.
don't think so. Oh, size. Sorry, yeah. I'm going to rename size. Is anything else depending on it? Because
Yes.
right.
Yeah, but maybe we should rename it later. But yeah. Let's do it after the live.
I'll leave it later. Yeah. Okay. And we're going to make sure that it is okay. So we could check that it's 5. However, I've told it to evict when it gets to 5. So the length is actually going to be 4. So what I'm going to do is I'm going to change how the eviction policy works. So yeah, I think probably we should just go for 1 higher than the capacity, because then that will actually allow us to remove the last entry. Okay.
What's saturating sub?
So that's just going to take 1, but if the capacity is already 0, it'll do nothing. Although that's going to panic anyway, isn't it? Because it's already expecting an entry when no entry is going to exist. Oh well, it's going to panic anyway. Might as well. We probably want it to panic on the bit that actually gives us an error message, so I'll leave it like that. Shit, what did I do? Excuse my French. Right. Testing. Oh yay, it's going to take some time to compile stuff. So, while we're at it, I'm going to also create a secondary test.
Should we actually test that the ones that are remaining, or yeah, all right.
So what I'm going to do is I'm going to test eviction updating. So in this case, I'm going to create the same 10 transactions, but what I'm going to do, actually I'm going to create 8 transactions. So I'm going to take the first 4 and insert them, then I'm going to take the second 4 and insert those, but right in the middle of this, I'm going to fetch the first transaction that we had. So that is the signature, isn't it? That should be fine. Where are we? Yeah, that's fine. And then afterwards, what failed? Expected child entry to exist. Okay, so it doesn't seem like it's the case that the child entries will always exist, so I'm going to remove that for now.
That's weird.
Let's just take a quick look at it again. I think it only does it for the trunk and branch of the transaction you insert. So you can insert a transaction that doesn't, or rather that doesn't have anything referencing it, in which case I don't think it'll have an entry.
Okay.
So what I'm doing here is I'm going through all of our transactions. I'm inserting the first 4, and normally at this point, if I were to insert the second 4, then it would evict the first 3 because we've got a capacity of 5. However, if I fetch this first one, then it should make sure it stays alive for longer and still remains within the tangle even after inserting these last 4. So now we can assert that it exists. And hopefully this doesn't fail, because otherwise I'm going to spend 20 minutes slamming my head against the wall trying to work out why. Oh, that's just me being stupid. And it failed. Let's see. see. Okay, so we gave it a capacity of 5, and the capacity was not 5, it was 4. So what happened there? That should be fine. I'm actually gonna make sure that the cache size is the same as the size of the rest of the tangle. Maybe someone in the chat can notice something I've messed up. Right, so they were both the same. Oh, I shouldn't be removing one there because I'm already adding one previously. There we go, that seems to pass. That's good, because it would be a bit embarrassing if I couldn't get it working on the live stream. I was worried for a moment. But yeah, so that demonstrates now that we have a simple eviction policy which should continue to work. It's not all that efficient, it has quite a few issues. I'm gonna, how long we've got 5 minutes. I'm gonna try to fix one of them now, which is performance related. So I'm going to create a new method that gives us the capacity of the tangle. This is a bit of a weird one because I don't really want to be locking this queue again to find that, so I should store it elsewhere, but for now, in the interests of brevity, I'm going to do so. So now we've got the capacity. So now when we're fetching a child, we only want to perform this update if the queue index, or rather the cache index of the entry is starting to get close to the eviction point, in which case we want to save it from eviction. And if it's not all that close, then we don't care that much. I don't think I'm really going to get time to implement this in the last 5 minutes because it requires altering the metadata of the transactions and so on. So I guess we could go to questions, or unless anyone else on the stream has anything to say.
Nope, sounds good. Did we actually do a test to check that all the remaining hashes are the one they should be?
So we've checked
because
that
you check only one at the moment.
Right, yeah, so what we can do is, I don't think we have a way to iterate over transactions in any meaningful order, do we?
No, I'm not. Yeah, I'm not sure you have a way to do that. But maybe in your
Right.
test you could store them.
Well, it's within the crate anyway. So what I can do is I can do for actually, does dash map even support iterating by values? I'm not sure it does. It only support. Okay, it supports iterating in general though. And then it's the fourth entry onwards. Yeah, that's kind of weird. Let's see whether the compiler accepts that. Oh my God, it
That's
does.
wild.
Oh no, it doesn't.
That's wild.
Yeah, it's a bit fucking. Excuse me, it's a bit nuts, really. There we go. That should. Work just fine. Oh. Well, that should remove the first one. Or the second one. Okay, so try this. Ref multi.
I think it's key and value. I think it's key and value and not zero or.
Oh yeah, I'm seeing that. I'm just looking at the thing now. So yeah, it's a bit of a strange API actually. It's a bit unconventional, I think, but oh well. Hopefully it works. Woo, that did actually work. So that's nice to see.
Awesome.
So basically, what we're doing here is we're checking that for each of the vertices in the tangle, they're either equal to the transaction that we newly pushed to the top of the cache, or it's equal to one of the last four transactions that we inserted. And it is, or rather they all are, which is nice. So yeah, that seems to work. Does anyone have any questions?
Oh,
cool.
Right on time.
Yeah.
Yeah, so in the chat, if you have any questions for us, that's
I see
the
Yanis
moment.
there with get vim. Yeah, I probably should.
Well, that's debatable.
So I'm just going to commit this. Okay. If nobody has any questions, then I guess that's the stream over. Nice to see you all.
Yep, and see you next week for
Yeah.
a new episode.
Bye, everybody. Thanks for watching. See you next
Thanks.
time.
Cheers.
Cheers.